In the previous video, I started drawing some structures where bonds were demonstrated. What are bonds? Atoms are connected to each other by bonds. Bonds are the glue that hold atoms together. In order to determine what constitutes the glue, we must discuss electrons. And so first we're going to review atomic structure. Atoms contain a small, dense nucleus made of neutrons and positively charged protons. This dense nucleus is surrounded by an extranuclear space containing the electrons. These are negatively charged particles. They are attracted to the nucleus by simple electrostatic forces. Most of the mass of an atom is contained in its nucleus. An atom is described by its atomic number, which is the Z number, which is the number of protons it contains, and by the A number, which is known as the mass number, which is the number of protons plus neutrons. All the atoms of a given element have the same atomic number. Isotopes are atoms with the same atomic number but different mass numbers. So the same Z number, but different A numbers, because they differ in the number of neutrons. The atomic mass or atomic weight of an element is the weighted average of an element's naturally occurring isotopes. Remember, electrons are delocalized or dispersed around this positively charged nucleus and are relatively massless. The electrons are where organic chemistry comes to life. So if the electrons are where organic chemistry comes to life, we have to discuss where these electrons are located in an atom. A shell defines the probability of finding an electron in a particular region of space relative to the nucleus. The energy of the electrons in the shells is quantized. Quantization means that only specific values of energy are possible, rather than a continuum of values. These shells occur only at quantized energies in which three important effects balance each other. The first effect is electrostatic attraction, which draws electrons toward the nucleus. The second effect is the electrostatic repulsion between the electrons. So most atoms have more than one electron, and these negative charges are going to repel each other. The third effect is the delocalization of electrons. Electrons have a wave-like nature and a particulate nature. The wave-like nature of an electron prefers it be delocalized or spread out so that the electron density spreads away from the nucleus. Delocalization is an important concept in organic chemistry. It describes the spreading of electron density over a larger volume of space. What we are going to see is that the quantized arrangement of electrons is where you have the greatest stability, where these effects are balanced out. And what we are going to see is that delocalization really does help drive stability. It lowers the energy. Electron shells are identified by principal quantum numbers, 1, 2, 3, and so forth. Each shell can contain up to 2n to the second electrons, where n is the number of the shell. The first shell can only contain 2 electrons, the second shell 8 electrons, and the third 18 electrons. In organic chemistry, we are going to be dealing with the n equals 2 shell primarily. Electrons in the first shell are nearest to the positively charged nucleus and are held most strongly by it. These electrons are lowest in energy. Electrons in higher numbered shells are farther from the positively charged nucleus and are held less strongly. Shells are divided into subshells, also known as atomic orbitals. Depicted here are the 2 atomic orbitals that we will deal with primarily in organic chemistry. This is a region of space defined with respect to the nucleus of a given atom. Two examples here are the s orbital, which is spherical, and the p orbital, which has two lobes. There are three p orbitals, which are oriented on the x, y, and z axis, so that we have 2px, 2py, and 2pz. Each atomic orbital can hold 2 electrons. The ground state configuration is the electron configuration of lowest energy. Remember, lowest energy equals the most stable. So it is the most stable configuration of an electrons for an atom. We can predict the ground state configuration by following 3 rules. So if you remember, the rules are as follows. The 3 rules are the Aufbau principle, the Pauli exclusion principle, and Hund's rules. The Aufbau principle, or the build-up principle, means that orbitals fill in order of increasing energy from lowest to highest. The order is 1s, 2s, 2p, 3s, 3p, 4s, and 3d. The Pauli exclusion principle states that only 2 electrons can occupy an orbital and that their spins must be paired. Here remember that just as the Earth has a spin, electrons have a quantum mechanical property referred to as spin. A given electron can exist in only 2 different spin states, spin up and spin down. Spins that are paired are opposite in sign. Hund's rule has 2 parts. First, if when orbitals of equal energy, which are degenerate orbitals, are available, but there are not enough electrons to fill all of them completely, the 1 electron is added to each orbital before a second electron is added to any of them. Second, the spins of the unpaired or single electrons in the degenerate orbitals should be aligned. The picture above depicts the electron configuration for carbon. This is the ground state configuration, or the lowest energy configuration. You have 2 electrons in the 1s orbital, and then 2 electrons in the 2s orbital. There are 2 more electrons in the p orbital. So now this is where Hund's rule will apply. These orbitals are degenerate. They are equal in energy. Because they are equal in energy, we will put 1 electron in each orbital and the spins will be aligned. Chemists often focus on the electrons in the outermost shell of the atom because these electrons are involved in the formation of chemical bonds and in chemical reactions. Outer shell electrons are called valence electrons. The energy level in which they are found is called the valence shell. Valence shell electrons are important because they participate in covalent bonds and they participate in chemical reactions. Carbon has 4 valence electrons. Remember, the number of valence electrons can be determined by the group number. According to the structural theory of matter, each element will form a predictable number of bonds. In general chemistry, you learned about the valence of an atom. The term valence describes the number of bonds usually formed by a given element. Carbon generally forms 4 bonds. Nitrogen generally forms 3 bonds, and oxygen forms 2 bonds, and hydrogen and halogens form 1 bond. Remember, Gilbert Lewis observed the chemical inertness of the noble gases, and he found that these noble gases have a stable electron configuration with 8 valence electrons. This led to what is known as the octet rule, where atoms tend to react in ways that achieve an outer shell of 8 electrons. The exception would be hydrogen and helium, which react to have a complete valence shell of 2 electrons. So if we look at carbon, carbon has a propensity to form 4 bonds. It has 4 valence electrons, and an octet would result in 4 bonds. Nitrogen tends to form 3 bonds. It has 5 valence electrons. So therefore, it achieves its octet with its 3 bonds. Oxygen has 6 valence electrons. In order to achieve an octet, it can form 2 bonds. Hydrogen has 1 valence electron, so it needs to achieve 2. It forms 1 bond. The halogens have 7 valence electrons. They want an octet, so they form 1 bond. Before we conclude the video, let's work on a problem. Problem 1.4 from the text states, write the ground state electron configuration of oxygen. How many valence electrons and how many core electrons are there? Oxygen is found in the n equals 2 shell. There are 2 electrons in the 1s orbital, 2 electrons in the 2s orbital, and 4 electrons in the 2p orbital. There are a total of 6 valence electrons. The valence electrons are found in the n equals 2 shell. There are 2 core electrons, and those are found in the n equals 1 shell.